Hello friends, welcome back to our YouTube channel. If you like this video, please like, share and subscribe. I'll share our videos commanded by our experts, so let's begin.
If you like, please like, share and subscribe. So let's begin our today's topic. Let's begin.
Amazon recently pulled the plug on its internal developer leaderboard. The dashboard, known as KiroRank, was built to track engineering productivity. Instead, it became a massive financial liability. The company had set a strict baseline. 80% of its software developers were expected to use generative AI tools every week. Across the Seattle headquarters and global engineering hubs, the workforce successfully logged in and hit that target. But as the adoption metrics went up, Amazon's cloud computing expenses spiked straight alongside them. None of that increased spending translated into new features, faster software, or additional revenue. We are looking at what happens when a tech giant ties employee performance directly to raw AI consumption. When you measure inputs instead of outputs, you don't generate productivity. You build a machine that burns money. Traditional software licensing is highly predictable. A company pays a flat annual fee for a seat, and the developer can use that tool as much as they want. Generative AI operates on a pay-per-token model. Every time a developer types a prompt or generates a line of code, an API call is made to a large language model. Each word, or token, processed carries a distinct marginal fee. Those API calls don't happen in a vacuum. They trigger massive GPU server nodes on the back end to execute the logic, drawing expensive compute power. Amazon's internal platform tracked these specific metrics. It evaluated engineers based strictly on the volume of tokens they consumed. This creates a major FinOps vulnerability. A flat-rate license caps your cost. A pay-per-token model has no ceiling. If usage metrics go unchecked, the financial liability scales indefinitely. Over the last 2 years, the technology sector has been defined by severe corporate layoffs and aggressive workforce reductions. Inside Amazon, developers were looking for any way to prove their value and secure their roles during a period of deep job insecurity. Management wanted a workforce embracing AI. Employees saw a leaderboard tracking their AI usage, and they artificially inflated the one metric they could control. Tech workers in Silicon Valley have a specific name for this behavioral exploit. They call it token maxing. KiroRank was built to measure productivity. The engineering floor treated it as a survival ranking. When an organization manages through fear and a single quantitative metric, the workforce will optimize exclusively for that metric and abandon their actual jobs. The primary vehicle for this widespread token maxing behavior, as discovered across the engineering floor, is the deployment of completely pointless automation. Engineers bypassed their codebase, instead deploying autonomous bots to execute trivial tasks directly through the API. These continuous looping scripts processed completely unnecessary text, logging massive volumes of tokens while the actual product codebase remained entirely untouched. The developers took the company's AI tools and weaponized them against its own financial operations, building engines dedicated solely to metric generation. This chart tracks the financial impact on AWS billing. Align plotting infrastructure costs and API volume rockets exponentially as millions of unnecessary calls hit servers daily. Meanwhile, a second line tracking functional code shipped flatlines completely. This artificial traffic consumed highly constrained GPU compute resources that should have been running actual product logic. The data confirms a complete separation. Metric growth went straight up, while business value stayed totally static. This is the ultimate cost of token maxing. Operational expenses scale linearly to infinity, while the actual return on investment drops to absolute zero. Amazon's senior vice president Dave Treadwell eventually intervened. He deprecated the dashboard and issued a firm internal memo instructing staff to stop using AI simply for the sake of using AI. The company is now restructuring its engineering KPIs, shifting focus entirely away from data consumption. The new tracking metric is called normalized deployments. Measurement now happens strictly at the end of the software pipeline. This shifts the entire strategy from measuring inputs, like API calls, to measuring outputs. A project has to actually ship to a customer to count. True engineering productivity is determined by the functional code that reaches the end user, not the volume of compute power burned to write it. Amazon's dashboard failure highlights a systemic vulnerability across the wider tech sector. Internal teams at Meta have struggled with identical behavioral loops, finding developers bloating data usage metrics to appease management mandates. Salesforce has faced the exact same friction when trying to track and force the adoption of their internal AI tools. For financial operations teams and engineering managers, the introduction of generative AI requires a completely different approach to oversight. In an ecosystem built on pay-per-token APIs, leaders must decouple developer evaluation from raw AI consumption. If they don't, they risk catastrophic financial drain driven by the exact employees they are trying to optimize.
Amazon ordered its engineering workforce to embrace artificial intelligence, setting a target for 80% of its developers to use AI tools weekly. But instead of a productivity boom, the mandate created a crisis that forced the company to abruptly shut down its own internal tracking system. The shutdown was accompanied by a direct memo from Amazon Senior Vice President Dave Treadwell. His directive was simple: please don't use AI just for the sake of using AI. To enforce the 80% adoption goal, management had deployed an internal leaderboard known as KiroRank. This system evaluated developers on the company's Kiro platform using a single metric: the raw number of AI tokens they consumed. This split-screen chart illustrates the immediate outcome. On the left, you see a massive spike in API tokens consumed by the engineering teams, but on the right, the line for actual code deployed remains completely flat. That rising line on the left represents a rapidly compounding financial liability. Advanced generative AI models operate on a strict pay-per-token basis. Every single prompt sent to the model incurs a fractional cost, and this specific volume of requests caused infrastructure and GPU computing expenses to skyrocket. The divergence between these two charts was driven by a specific behavioral adaptation that Silicon Valley tech workers have dubbed token maxing. Rather than writing software, engineers were deploying autonomous bots and AI agents to execute trivial, repetitive, or entirely unnecessary tasks over and over again. None of this automated traffic produced business value. It was generated to pump up data consumption numbers and secure a higher rank on the KiroRank leaderboard. When an enterprise engineering team measures performance by tracking raw AI data consumption, they break the standard mechanisms for evaluating software engineering. They reward the act of consuming compute power rather than the act of building software. To capture actual return on investment from generative AI, engineering organizations must abandon these input-based metrics and transition to frameworks that measure functional output. To see why a volume-based leaderboard fails, we have to look at the unit economics of large language models at the base layer. Unlike traditional software tools installed locally on a machine, processing data through an LLM requires external server calculation. Every individual word, snippet of code, or image generated by a developer carries a direct, calculable computational fee. This creates a structural tension between corporate financial goals and the specific behaviors a leaderboard encourages. By overlaying a competitive ranking system onto this pay-per-token cost structure, management tied employee success directly to the massive volume of data requests they could forcefully push through external servers. Mathematically, this system offers zero reward for an engineer who writes a concise algorithm without assistance. It explicitly incentivizes developers to maximize infrastructure overhead instead of coding efficiency. In a pay-per-token ecosystem, gamifying AI consumption is functionally identical to gamifying company expenses. The developers who flooded the network with artificial traffic were simply operating rationally within a highly competitive, high-pressure environment. At the exact same time management issued the mandate for 80% AI adoption, the entire tech sector was experiencing heavy corporate layoffs. Under the threat of losing their positions, engineers felt pressured to prove they were embracing the new technology. Inflating their token counts was a defensive strategy to secure their jobs. This diagram outlines a structural breakdown known in economics as Goodhart's Law. It starts on the left with job security fears, which drives the behavioral node, deploy autonomous bots. Those autonomous bots funneled directly into a central LLM API hub, constantly pinging the servers with requests. Every request processed by that API hub triggers a pay-per-token fee, which continuously drains the GPU infrastructure budget on the far right. The result is a closed loop, where highly advanced, expensive compute resources are continuously deployed to solve problems that are already solved.
British economist Charles Goodhart stated that when a measure becomes a target, it ceases to be a good measure. By targeting token volume, the system actively degraded the engineering environment it was meant to optimize. Recognizing the failure, Amazon deprecated the internal dashboard and shifted its evaluation metrics away from raw data toward tracking what they call normalized deployments. An output-based strategy evaluates developers on whether they are successfully utilizing AI to write useful code and ship functional projects to users. When shifting away from token usage, the most obvious alternative metric is counting the raw lines of code produced by a developer. But this is a false alternative. Large language models are highly proficient at generating text. If engineers are evaluated by line count, they can use AI to generate thousands of lines of useless bloatware boilerplate in seconds. Tracking lines of code presents the same trap as token maxing. Both are volume metrics that offer zero guarantee that the resulting software actually functions. Authentic productivity measurement demands evaluating the velocity and stability of functional software units, rather than the raw volume of text produced to build them. This pipeline diagram illustrates the specific architecture required for tracking normalized deployments. A block of code moves linearly through 4 stages: commit, automated testing, staging, and finally, production deployment. The first key variable in this framework is deployment frequency. This measures the rate at which code successfully clears the automated testing node and reaches production. The second variable is lead time for changes. This calculates the time delta between a developer's initial commit on the left and its final functional deployment on the right. This metric captures the logic of AI leverage. The tools must reduce this lead time. If the lead time remains static despite heavy AI usage, the AI is functioning as administrative overhead, not a productivity multiplier. The final safety variable is change failure rate. This tracks whether the AI-generated code being pushed through the pipeline is introducing bugs that require rollbacks once deployed. The normalized aspect of this framework means that these 3 metrics are mathematically adjusted based on the complexity of the specific project the engineer is assigned to. Applying this adjustment ensures that developers cannot game the system by submitting dozens of tiny, meaningless software updates just to pad their deployment frequency. This architecture rewards engineers for shipping functional products, aligning developer incentives with business value. Amazon's KiroRank failure reflects a broader industry-wide trend. Organizations like Meta and Salesforce are fighting similar battles against artificial data bloat, where employees inflate usage metrics to satisfy management mandates. This graph shows what an ideal operational state looks like. Instead of divergence, the line for AI tokens used and the line for successful code deployments are tightly correlated, moving upward together as genuine productivity increases. Artificial intelligence is a leverage tool for problem solving, not a raw manufacturing material to be stockpiled. Measuring the raw tokens a developer uses is like measuring the mechanical advantage of a lever without checking if anything was lifted. What matters is the actual weight they move, which in software means shipping functional features. The engineering organizations that successfully navigate the generative AI era will be those that align their measurement architectures with end-user value, incentivizing developers to solve real business problems rather than simply feeding the models.